Good day, everyone. My name is Fausto Vaninetti, working for Cisco Systems as a Senior Technical Solution Architect. And a few years back, I served in the Board of Directors of SNIA Europe. Today, I am very pleased to be here with you, and I want to thank you for joining and listening into my session, where I will try to describe an innovative fabric-centric SAN congestion solution called dynamic ingress rate limiting. The agenda is pretty simple. I will describe and introduce what is SAN congestion. I will describe the existing solutions to address SAN congestion, and then I will introduce the key concepts and operation for dynamic ingress rate limiting. I will conclude my presentation by going through the benefits of DIRL. When you have a network with a nominal speed that seems to be sufficient, you need to be aware that the nominal speed might not be really available to your applications because of congestion. This is the same that happens with roads when there are too many cars around. So if your network is congested, applications will see a slowdown. Fibre Channel is accredited and no-drop fabric. And this is very good because it's a highly available, high-performance, predictable, and storage-friendly fabric. But at the same time, one single congested port can cause back pressure and propagate congestion backward toward the source via the interswitch links, impacting the entire fabric. There are two types of congestion scenarios. One is described as the classic slow drain. Classic because it's pretty old, and it's still very popular. In this case, end devices withhold buffer-to-buffer credits and receive-ready primitives, slowing down the rate of data transmission and causing congestion. At this point, congestion works its way back across ISLs toward the data source. If you want to detect a classic slow drain situation, you can look at the frame transmission wait time on F ports, and this is possible with ASIC level counters. The solution to classic slow drain would be investigating the end device for internal bottlenecks. For example, you might have a misbehaving HBA, or the CPU of your server could be very busy with an antivirus solution or some other task. The other scenario for congestion in a storage area network is called overutilization. And on F ports, this means that end devices would be requesting more data that can be transmitted to them. But buffer-to-buffer credits and receive-ready primitives are not slowed down and would behave normally. On E ports, overutilization means there is insufficient bandwidth in the storage area network. Now, this scenario is quite uncommon, but theoretically absolutely possible. So in both cases, data transmission will be at or near 100% of the nominal link speed. Host overutilization is on a growing trend. The adoption of all-flash arrays without a corresponding change in the storage area network design or a refresh of the compute farm is creating a lot of overutilization situations. And it's more difficult to detect because here we need to take into consideration a couple of parameters. First, we need to consider high link utilization, and then we need to correlate with significant back pressure toward the source. Now, high link utilization is detectable using ASIC level counters. The frame transmission rate can be measured that way, and it is possible to do so for the steady state or bursts. The solution to host overutilization is to increase the HBA capacity, having more HBAs or improving their port speed. The solution to overutilization on ISLs is just to add more ISLs into the fabric. Now, what I just described in words is depicted here in a graphical format. On the left, you have the host link over utilization scenario. On the right, you have the classic slow drain scenario. Look at the left. You can immediately understand that something could go wrong in this solution. In fact, the host is connected with an 8 gig port, whereas the all-flash arrays are connected using 16 gig ports. Now, imagine if the host is asking for data, the all-flash disk array will immediately respond with all the data toward the host. And in this way, it will saturate the host link. This is a typical example of host link overutilization. Now, if we want to understand the situation a bit better, we need to look at parameters, ASIC level parameters on the switch side for the host link. You will notice that the transmit utilization on the host link is near 100%. The link is working at its maximum capability. But if you look at the buffer-to-buffer credits, which means if you look at the EX wait time for frames on the link, it is pretty low. So there is no buffer-to-buffer credit starvation. Now let's contrast and compare to what happens in the classic slow drain scenario, where we have a device that is intentionally misbehaving compared to what is expected from him. And the other devices connecting to the same fabric are just innocent. They are impacted, but innocent. The culprit is a device that is not responding properly to Fibre Channel frames in the sense that it's not ingesting them at a normal rate. It's releasing receive ready indicators in a slower than expected way. And in this case, if you look again on the metrics on that host link, you will realize that the link utilization is normal. It's not close to saturation. But if you look at the buffer-to-buffer credits, you can see that there is starvation. Now, if you consider the ISLs, you will see exactly the same situation in both scenarios. The ISL is underutilized and there is buffer-to-buffer credit starvation. So what I'm trying to say is that the distinction between host link overutilization and classic slow drain cannot be seen from ISLs, but it needs to be determined by looking at specific F-port ASIC level counters. And that's the way you will find out the difference. Over the years, multiple solutions have been implemented to address, solve, mitigate, alleviate sun congestion, both the slow drain and overutilization type. First attempt was called frame dropping, and it's pretty intuitive. Within Ethernet networks, when there is congestion, you just drop some packets. But the TCP protocol is able to handle that. On Fibre Channel networks, if you try to drop frames, yes, you're going to fix the congestion problem, but you are heavily impacting your applications. Storage applications, SCSI level applications, they don't like when frames get lost. They have long timeout before they make an action and remediate. So the frame dropping approach to eliminate congestion in a storage area network is not really very good. Another approach that was conceived and introduced a few years back is using virtual lanes. The spirit of this approach is based on something similar to what happens on highways. You can put different vehicles, depending on their speed, on a different lane. For example, slow vehicles on the right and fast vehicles on the left. Now, the problem with this approach that can be applied to storage area network as well is that, first of all, you require inter-switch links in order to make this operational. And second, even if you have divided your frames into multiple lanes, you are not able to solve congestion within a single lane. So this solution is okay, but not perfect. Both of these solutions I just described try to treat the system symptoms, but more recently, new solutions emerged trying to treat the causes directly. And the INSIST T11 standardization body that is behind the Fibre Channel protocol has introduced something called FPIN, Fabric Performance Impact Notification and Congestion Signals. This solution looks very nice and very promising on slides, but it's a collaborative approach, which means that the network and the end devices need to talk to each other and exchange information, which means the entire ecosystem needs to be compatible with this solution. It needs to speak the FPIN language. And right now, this is not the case. FPIN is supported on network devices. It might be supported on very recent HBAs, but it's not yet supported on storage devices. So maybe it will be a good solution, but not for now. We need to wait a little bit more time. And that's why another proposal was made. And this is called dynamic ingress rate limiting. The main benefit of this solution is that it is HBA independent, which means there is no interoperability metrics. It's a fabric-centric approach, and it doesn't require any exchange of information with end devices, being their servers or targets. In many cases, simple ideas have the greatest impact. And let me tell you this story, which is not very commonly known. In ancient days, people used to write using the Roman style, which is all capital letters, essentially. And you can still see this style on the epigraphs and the text on ancient churches. Now, the problem with the Roman style is that you need to detach the pen from paper before you write the next letter. And this slows you down. That's why during the Renaissance, an Italian humanist introduced a different style, and it was coming from a simple idea. The idea is, if I don't detach the pen from the paper, I will be able to write faster. This new approach has become the italic style, and it's normally used when you write, when you do your handwriting, but it's also used on computers. So that was a simple idea with a great impact. Now, the DIRL is something similar. Simple idea, but great solution. Now, to describe the solution, I need to describe a couple of concepts. The first one is that in Fibre Channel world, every operation is a single exchange. And every exchange is built with multiple sequences, and every sequence is built with multiple frames. So all the data, when using SCSI or NVMe protocol, is solicited. You need a trigger. There is no autonomous transfer of data on a Fibre Channel network. And now the trigger could be a SCSI command read, or it could be, for writes, it would be a transfer ready. So independently from what is specifically your trigger, you need a trigger before data starts moving and crossing the network. Second concept I want to introduce is static ingress rate limiting. Majority of switching devices have the capability to set a static limit for the ingress rate of frames. And the way it works is by slowing down the buffer-to-buffer credits toward end devices. It's an ASIC level capability. And so it depends on the ASICs. Not everyone is doing something identical, but more or less it's a pretty common capability. Practically, it means that you have a nominal port speed of 32 gig. You could set an ingress rate limiting down to 10% of it. which means you will be able to ingest frames up to 3 gigabits per second only. And when the ingress rate limit is applied, all frames are rate limited, including SCSI read commands and transfer ready indicators. Those are our triggers. So now let's put it all together. We have 3 premises and 1 simple great idea. Premise number 1. In fiber channel networks, data only moves when solicited. Premise number 2. Network congestion happens when there is excess data in the network that backs up in the direction toward the source. And we have 2 types of congestion, called classic slow drain and overutilization. Premise number 3. Ingress rate of frames can be controlled and limited by applying a rate limit. Now, the idea is that by reducing the ingress rate, we can reduce the egress rate. In fact, by reducing the ingress rate of frames, the rate of I/O solicitation requests will decrease, resulting in a proportional reduction in egress rate of frames and virtually eliminating congestion from the SAN. Dynamic ingress rate limiting determines no packet drops, and this is very, very nice. It is dynamic because the ingress rate limit is adjusted. It can be reduced but also increased depending on the condition found in the network. And only the slow draining or overutilized devices are affected, not multiple devices in the fabric. It works topology independent. You can have ISLs, you can have a single switch with no ISLs, you can have any protocol like SCSI or NVMe over Fibre Channel. This dynamic ingress rate limiting solution works in all cases, and no modification is required on hosts and targets. Now, another possibility to describe the DIRL can be seen by comparing the behavior before and after, when the DIRL is disabled or when the DIRL is in action. I will not really describe in detail what you see here on the slide, but there are webinars that you can listen to, and there are blogs that describe the feature in more detail. Essentially, when the DIRL is in action, the culprit, the device that tries to monopolize all network resources, is prevented to do so. And the other nodes keep talking at the same level as before, so they are not impacted. Another way to describe this solution is to talk about noisy neighbors and the way to make them silent. In summary, the DIRL benefits are multiple. First of all, the effect is limited to slow draining or overutilized links. Other related devices, such as devices that are part of the same zone, are not affected at all. And there are no packet drops. The guilty device will underperform for sure, but it will not experience errors due to packet loss. And by dynamically adjusting the ingress rate limit, we can also go back to normal situation when congestion disappears from the network. And this is very useful for devices that are only temporarily slow draining devices. The DIRL can work with any topology, tiered SAN with ISLs or single switch SAN. The determination of the slow drain or overutilization situation and the rate limiting action happen on the same switch and the same switch port. There is no dependency on HBAs, there is no interoperability metrics, and you can work at all speeds independently from the features that have been configured on the host side. No modification is needed on hosts and targets, and no license is required. Of course, it is best to use 32 gig or 64 gig switches just because they have an optimized rate limiter or a faster control plane. That's the end of my presentation. Hopefully it was interesting to you. Please take a moment to rate this session.